Okay, well, this presentation I think is fairly relevant to amateur radio operators. I started out my interest in radio and radio propagation started out as being a shortwave listener in the 1950s, and I've basically come the full circle. I'm now a shortwave listener again, except the waves are much shorter than they were in the 1950s. So, what is amateur deep space reception? There are quite a few challenges associated with it. S-band and X-band systems are the most common. S-band being a bit below the amateur 13 centimetre band, around 2 gigs, and X-band is between 8.8 gigs and 8.5 gigs. So they are the most common. There is the KU band at 32 gigs, and there's one amateur deep space reception operator has actually got a 32 gig system, and that is it's an English station, and that's certainly quite something to do, quite cutting edge by amateur radio standards. Demodulation of science data, which of course is the whole science data is what is being transmitted. It can be demodulated in the amateur sense, but it's difficult. But it has been done with the spacecraft that are closer to Earth. The Yahoo Group Amateur DSN is the focal point of activity, and it discusses spacecraft signal reports and general technical chatter. Okay. Right, why would you want to do it? Well, there's all of these listed here, I think, are all very good reasons. Self-improvement from a technical perspective, and that really is one of the fundamentals of amateur radio. To learn about spacecraft orbital mechanics, and that in itself is a very interesting topic. I knew nothing about it before I started, and I still don't know really much about it, but it's very interesting learning about it. Learning how to build and optimize receive systems, which is the heart of any weak signal system, any weak signal endeavor. To learn about high precision frequency and time standards, to experiment with software-defined radio for weak signal detection. I had never had any experience with software-defined radio dongles before I attempted this, and I've really taken to it. And of course, to detect spacecraft millions of kilometres from Earth. Initially, I didn't really think it was possible for amateurs to have dishes in their backyards to be able to do this at all. In fact, I wouldn't have even thought amateurs could receive something from 1,000,000 K away. But I've got a screenshot later on, which will demonstrate that you can do much better than 1,000,000 K. What we're doing, of course, is from an amateur point of view, is we're competing. Anyone trying to do this, and this is a bit daunting. You're competing with 68, 70 metre dishes. A Canberra 64 metre dish. They have 3 dishes. At 8.4 gigs, has a gain of 73 dB. It weighs over 3,000 tonnes, and the half-power beam width is 0.04 of a degree. That's a 25th of a degree. So if you had all those increments in a circle, you'd have 8,000 of them at 0.04 degrees. So that's sort of that's enough probably to put anybody off trying to do it at home. But anyway, as we'll find out, it's not actually all that difficult. Okay. Now, there's a group of three professional DSN ground stations, NASA and ESA. ESA is the European Space Agency. They're the primary users of DSN frequencies, Deep Space Network frequencies. And apart from the three, the three are Canberra, Madrid and Goldstone. Goldstone is in California. And all with very big expensive setups. Yes, in fact, I've got it listed here. Sites at Goldstone, Madrid and Canberra. They've at least with 4 antennas, ranging from 26 metres to 70 metres. And these antennas operate in the 8.4 gig, 2 gig and 32 gig bands. NASA are moving towards 32 gig for greater transfer rates. And initially, say as recently as 10 years ago, NASA wondered whether 32 gigs would be suitable, given, of course, that it has to go through the atmosphere. And they sent up one spacecraft with it on as a beacon, not for transferring data, and it worked very well. It works as well as 8.4 gigs. There's absolutely no problem with it. So that's quite interesting. Okay. Funding for Canberra is paid for by NASA with an annual budget of $20 million, and their California base, the JPL in near Los Angeles and Pasadena, the annual budget there is $26 million, and I think I worked that out at $73 million a day to run it.
It is in fact billion, is it?
Canberra. The initial funding, the initial cost of the installation, which took place in 1965, that was also funded by NASA. And of course, the purpose of that at that time was for the upcoming moon landing, of which Canberra, in fact, Canberra was the first ground station on the planet to receive signals from that moon landing in July 1969. As I said, their dish weighs over 3,000 tonnes. It would have cost a lot of money even in 1965. Okay. Right, what is out there to detect? There are two types of space vehicles. Those orbiting planets, such as Mars, Jupiter and Earth, also the Moon and the Sun. And there are vehicles on the way to planets and asteroids, and that is known as being in cruise mode. Nice sort of term for something that will take a long time. The current time span to reach an asteroid, say, around 1 billion K away, is about 7 years. Distances involved: Mars currently around 300 million kilometres, Jupiter currently around 3 times that amount. Okay. Right, the equipment required at amateur level, well, nothing really very fancy. The bottom right is a 2.3 metre dish, and the reason I took a picture of it is actually owned by Wayne, 4WS. In fact, if someone wanted one, if they saw him, he probably might sell it. Anyway, I have a picture of that because dishes like that are readily obtainable from places like Sunnybank Hills, Tingalpa, because they were very common for satellite reception. In fact, you can just see there coloured white as a C-band feed for it. So 2.3 metres, is a pretty good size. I use a 3.7 metre simply because I've had one for nearly 20 years. But dishes as small as 1 metre are used incredibly. 2.3 or bigger is the norm. An accurate as elevation drive with position reporting to within, say, about half a degree. The dish will need a feed to suit right-hand circular polarisation. That is, the spacecraft transmit in right-hand circular, so the feed is built for left-hand circular, given that it changes as it's reflected from the dish. There's nothing very special about all this. A low noise preamp, well, a lot of people have got one, use one for say 10 gigs, 0.8 dB or better, there's 28 dB or more gain. You'll need a down converter from 8.4 gigs to an IF frequency, and a software-defined radio displaying waterfall results on a PC. The down converter, I use a Kuhn down converter, which has selectable IF frequencies. The IF frequency that I use is 1296, 1296 being a lot better than 2 metres or 70 centimetres because of the low image noise. So it's quite a good frequency to have. But nothing very special. I use the Kuhn converter, down converter. I have mounted right at the feed, and since it has a 0.8 dB front end noise figure, I don't need an external preamp. I do have a 0.8 dB preamp, which I initially used, but putting the converter up at the feed, I'm getting identical results. There's something else I was going to say. Yeah, nothing. I don't have any. I don't use any filtering. The mixer runs wide open. I don't use any GPS locking either, and as I said, I don't actually have a separate LNA. Okay.
You're not transmitting.
Right, well, this is a screenshot I took about a month ago. The SDR that I use is an AirSpy R2. I did a bit of research on what I should be buying, and the AirSpy had good reviews. I didn't actually know anyone that had one, but and I've been very pleased with it. And for me, an introduction to software-defined radio. So that's quite a good signal from 336 million K on my system. You can see a downward shift in frequency, and that particular signal is about 15 dB above the noise. Currently, Mars is approaching us at the rate of 500,000 K per day. So it will end up at about, it'll end up relatively close, about 160 million K. And that will take place later on in the year. So that's the sort of signal, that signal is fairly typical with an average system or not what I'd call a sophisticated system, nor a sophisticated operator. But it's a decent sort of, it's something very useful to work with. Okay. Right, critical aspects for success. Obviously, you have to build a system to overcome the hefty path loss. The DSN ground stations, Canberra being one of 3, There are other ground stations. There's one very good one in Western Australia, but they're not part of the DSN network. They typically receive in the 110, minus 110 dBm to the minus 150 dBm range. Accurate tracking and position reporting, about the same as you would use for EME. For calibration, the sun can be used, which is a very good way, or in a bigger system, thermal moon noise. On a 3.7 dish, I'm getting about 1 dB of moon noise, just as a black body radiator. So that is very good for maintaining sensitivity or checking that your sensitivity is what it was. And of course, it's also very useful for checking azimuth and elevation calibration. How it works is that how a signal originates from a spacecraft, it's initiated by a signal from the ground station. Now, they send up a pretty hefty signal on about 1 gig lower, around about 7 gigs. And this then triggers off the spacecraft, which will then downlink the information that they have stored during the whatever orbit they are being, whatever portion of an orbit they're being looked at. Typically, the ground station uplink is about 8 kilowatts to a 68 metre dish, so we've got a pretty hefty signal. Now, recently, a Canadian operator has just done something that I never ever thought of, and in fact, nobody had ever thought of. If you're aiming your 7 kilowatt S-band signal at a spacecraft orbiting the moon, you're therefore going to have that signal bouncing off the moon, and it would be a very good signal. So in that case, all you would need is, well, I say all you would need is a 7 gig receiving system, and that's being done successfully. So quite accidentally, the ground stations, or Canberra in this case, was, Goldstone in this case, was acting as a EME station. Now, carrier suppression with high data downloads. Just the last point I've got there first. From an amateur point of view, detecting the carrier is what we're after. In fact, it's the only thing that we're after. Now, unfortunately, the spacecraft may or may not downlink with a lot of carrier suppression, or in some cases, there's even no carrier at all. So it's like a bit like a single sideband suppressed carrier setup, and you never really know if you're going to receive this or not. Now, the screenshot that you saw previously, there are some days where you can track onto that satellite, even though you monitor what Canberra is doing. So you look at what Canberra is doing and say, okay, they're receiving a particular satellite. So we know the spacecraft is transmitting, so why can't we receive it? Well, sometimes you can and sometimes you can't. And it's all a function mainly of the rate or the amount of data that they are downloading from the spacecraft. The higher the data rate, the more carrier suppression. Now, some spacecraft will transmit all the time. They don't have to be triggered by anything. They are just transmitting data forever and a day. And they, of course, are ones that are easier, obviously, easier to detect. Okay. Right, how do you locate a spacecraft? There's a pretty big area out there. Sites such as DSN now will show you what Madrid, Goldstone and Canberra are doing. They've got pictures of their dishes and they've got indicators as to whether they're receiving or transmitting or doing both. And these sites show the current status of the spacecraft being communicated with. JPL Horizons. JPL is the Jet Propulsion Laboratory located in Pasadena, which is more or less a suburb, an eastern suburb of Los Angeles. Now, they very kindly give out a lot of information, such as pointing information, of course, visibility, range, and data, necessary data that you can make Doppler calculations with. They don't actually give you the Doppler correction, but they give what's called a del dot figure. And VK3XPD, Alan Devlin, has developed a very good spreadsheet to calculate Doppler. When I initially started with this, I knew what frequency they were on, of course, and I said, okay, Mars is approaching us, therefore the received signal is going to be higher in frequency than what they're transmitting on. And so I just hunted around with the SDR until I found something. Now, once I did that, I've logged everything, but then Alan Devlin has come up with this spreadsheet, and it's quite remarkable. I've done a lot of testing with it over the last month, and it is within 3 hertz accuracy. The predicted signal at my place or anyone's place is within 3 hertz of what the spreadsheet calculates. Now that 3 hertz could well be an error at my end, but nevertheless 3 hertz as a percentage of 8.4 gigs is, well, there's a lot of noughts associated with it. Information regarding spacecraft and their frequencies, that information is available online. Canberra issue paperwork or issue information about all of the spacecraft that they receive or all the spacecraft that they work with, both at 2 gigs and 8 gigs, and also 32 gigs. So that information is fairly readily available. But it's not something that you can just hunt around. You can say, okay, well, Mars is up there. I can actually, if I go outside, I can see it. So if I point to that and hunt around for frequency, I might come up with something. Well, you might, but you probably won't. Okay. That's it, is it? Must be. That's it. Right. Anyway, look, that's sort of a rough guide, a rough presentation, approximate presentation of what's required. I'd have to say that I was really intimidated by this before I started, and I was intimidated also psychologically by the prospect of getting into EME. But this reception of spacecraft 400 million K away is in fact not that difficult. When I say it's not that difficult to assemble the equipment required to do it. As I said, I don't use, no filtering is required, no GPS locking, not even a preamp. Basically, you have to know, there's 2 things you have to know, is where the spacecraft is, where to point it, and how much Doppler correction do I make. Now, they're really, there's a little bit more to that than meets the eye, but basically it's a pretty straightforward exercise. The picture there is, well, the planet Mars is real, and the picture of the spacecraft, which is the Mars Reconnaissance Orbiter, that's real, but it's been superimposed there to make quite a nice picture. Nobody took that picture. But,
Trevor, is the Coon down converter the only one that's available?
Sorry?
Is the Coon converter the only one available, or are there other?
Yeah. Oh, is it the only one available?
Yeah.
I think Down East Microwave makes something. There are people who have, look, there'd be plenty of talent in this room to homebrew one. There's nothing too special about a down converter. And many people have done. They've, got a mixer and got an oscillator and filters, but I went the Coon way because I have used quite a bit of Coon equipment in the last 30 years, and I found it to be very good quality. But this down converter that I got was really excellent. And the S-by SDR is pretty good too. It covers up to, I've forgotten the lower limit, but the upper limit is 1.8 gigs. So 1296 fits very well into that. But look, it's a fascinating thing to do. This is one of the best things I've done. There's plenty of challenge in it, and to me, a bit like hearing your own echo off the moon. To look at a screenshot, the one that we saw before, at something hundreds of millions of K away, and it's operating on this dish I've got out on the balcony. For me, is sort of quite makes it all quite worthwhile.
Trevor, will you comment on Voyager 1, Voyager 2?
Sorry?
Would you comment on Voyager 1, Voyager 2?
Sorry, but you have to speak up a bit, Doug.
Will you comment on Voyager 1 and Voyager 2?
Right, yes. Yeah, okay, thanks for bringing that up. Well, the Earth stations, good point. Now, Voyager 1 and Voyager 2, Voyager 1 has been transmitting continuously since 1976. And they've just recently got Voyager 2 going again, incredibly, which took 3 years of work. There's some smart people out there. You would think after being dormant for a long period of time, and given the fact that it's currently at 23 billion K away, the light time for that screenshot was 20 minutes. So the signal is 20 minutes old. The light time from Voyager 1 currently is, I think, about 28 hours. Well, you could work it out anyway. About 28 hours. If this is 20 minutes at 3:30, I know it's DSN called it a day and a half. They relate it to a day and a half light time. All right, well, Voyager 1 and Voyager 2, they are both equipped with 3.7 metre dishes. They were design of them started in the 60s, the late 1960s, and they were launched, I think they were launched in 1976. Originally thinking that they'd have a lifespan of 15 or 20 years. Well, they're going to go, what's 1976 to now is, well, nearly 50 years, and still going strong. They're nuclear powered. Of course, there's no sunlight where they are. 3.7 metre dish, originally equipped with 10 watt transmitters. They transmit an S-band around 8.4 gigs. The power of Voyager 1, the data tells us on the ground, that the power has gone from 10 watts to 8 watts. So Canberra currently are detecting Voyager 1 at around minus 155 dBm, which is fairly weak signal. But more incredibly than that, Voyager 1 has also been received by amateurs. Now, the first amateur to detect it was CT1, is it CT1DMK, Lewis Cupido, is that his call? Yeah. Right, he received it in 2003 when the range was 13 billion K away. He received it on a 16-foot dish in his garden, surrounded by lettuces and things. He had a linear feed, so there was a 3 dB hit there right away, and the time taken was about I think about 15 minutes. I've just forgotten the word. What's the word for integration? Is it? Yeah, yeah. Took about 15 minutes of integration. Now, initially he thought, well, is this the real thing or not? And maybe this is some artifact I'm receiving. So he sent all his results to 2 or 3 experts around the world. And one was in Japan, a well-known amateur, I don't know the call, also one in England, James someone, who is very well up in this. And they analysed his results and were able to confirm that he was listening or detecting the real thing on a 16-foot dish. Quite unbelievable. Further, a more recent detection was a group of German amateurs about 3 or 4 years ago, with a big dish. They had access to a 20-metre dish, and they did it, three German operations. I think it was a 20-metre dish, and they were able to duplicate what Lewis Cupido had done. But except that by this point it was over 20 billion K away, nearly double the distance. So doubling the distance would be 6 dB, more difficult. So that's but very few people, I think it certainly would be well beyond my technical and intellectual expertise to even consider doing something like that. And there's very few people in the world that would be qualified to achieve it. But nevertheless, a remarkable achievement. What is upcoming, which will be very interesting, is the next manned moon landing, which was originally scheduled for later this year. It was put back to next year, 2025, and I just recently read where it's been put back further to 2026. Now they're going to be using still the 2 gigs S-band, 2.2 gigs, as was used in the first moon landing in 1967, and the link between the moon surface and the orbiting spacecraft will also be the same as before, which is 400 megs. So you've got that link, and then the orbiting spacecraft will relay the transmissions back to Earth same as they did in 1967. I understand that in 1967 that the 400 meg link between the surface of the moon and the spacecraft was actually able to be copied on Earth by amateurs as well. So that was sort of quite interesting. There was some amateur, including Australian. Somebody might know better than myself, but there were Australian amateurs that were involved in spacecraft reception in 1967. Well, it'll be a whole lot different this time. 2 gigs then, I presume, was relatively cutting edge. Well, perhaps not cutting edge, but fairly advanced for by amateurs uh, in that time frame. But nevertheless, it's generated a lot of interest in amateur reception because this time everyone will be prepared, and it should be quite a formality. I mean, detecting a signal via moon bounce is quite easy. So this time we can eliminate signals coming back from the moon, reflected from the moon, only about 7% of what it receives. Well, this time there's none of that. It's just a straight line of sight of up to about 400,000 K, which won't be a problem. We can receive this at 336 million K. Half a million or a third of a million K won't be a problem. Okay, well, look, I think I've, 38 minutes. I think that's probably about all I've got to offer, unless anyone else is.
That signal you're looking at there was just pure carrier, was it?
Sorry?
That signal that you showed there was just pure carrier. There was no data on that one at all.
Yeah. Sorry, just speak up a bit.
The signal there was just
pure
carrier, no data.
Yeah, that's correct. Yeah, that is carrier detection only. The sidebands of that signal would contain data, of course. And one of the spacecraft that I received, the sidebands showed up very well in that screenshot. But analysing the data, there's one spacecraft called Stereo A. There were 2, Stereo A and Stereo B. Stereo A runs currently about 30 million K from Earth, which in deep space communication is sort of like the Brisbane beacon in the relative sense. And Stereo A collects data from the sun, what the sun is doing, and pictures of. And amateurs have received that, including not just the data, but actually ending up with a picture, and a picture of not bad quality, showing the surface of the sun and what's happening with it.
What sort of dish surface do you have on your dish?
The dish surface is a mesh dish. It's probably not ideal, I think, at this frequency. The dish I've got is just basically a TV dish.
TVRO dish?
Sorry?
TVRO dish?
Yeah, just a TVRO dish. I purchased it new in 2005 for just $360. There's a company I've just forgotten, Joysat in Acacia Ridge. This exact same dish today, they want $2,200 for. Now, my income certainly hasn't gone up 7 times. In fact, it's gone down. But so yeah, just a TVRO dish. There's quite extravagant claims made as to its gain at 12 gigs. So anyway, it's all I've got.
And it's working.
And my feeling is that if you, ideally what you'd want is a solid dish, which is likely to be more accurate and likely to be made for something a bit more sophisticated than television satellite reception from just 36,000 K away. But my feeling is that if I had a hotshot, very heavy solid dish, I don't know if that signal would be all that much stronger looking at the screenshot. I mean, you'd never know until you did an A/B test, but
That's plenty strong enough anyway, Trev, isn't it?
yeah,
That's plenty.
Yeah, that's plenty, yeah.
15 dB, that's
I mean, you
very
could take a 10 dB hit to that,
Easy.
you see, and
You've only just got to see it.
yeah, so
But if you tuned a BFO across it, would you get a whistle?
sorry,
Would you?
yeah, no, you don't hear that. No. A lot of the screenshots that I've had actually have shown no Doppler whatsoever. The Doppler, of course, can come from the Earth's rotation, irrespective of what's happening out there. But some of the screenshots I've got just show a dead straight line. The reason I included this one, which clearly shows a shifting frequency, was in case someone thought I was picking up a spurious frequency from a street light or something, or a door opener. And anyway, that's definitely, the source of that signal is definitely moving in relation to myself.
I just did some sums.
Yeah,
500,000 k's a day, 20,000 kilometres an hour.
is that 20,000 an hour?
5 kilometres a second.
Right, that's
What's
500,000
the
a day.
Doppler on that then? That must be pretty
Yeah.
funny. So what's the Doppler on a 5 kilometre a second body?
Yeah, okay. Oh, that's good, Peter.
What's the Doppler amount? You know,
Put it in the spreadsheet.
Look in the spreadsheet.
Yeah,
What is
yeah,
it?
good idea.
What is the Doppler shift? You know?
Yeah,
Tens of kilohertz, probably 100.
Yeah, it's hundreds of kilohertz. You wanted to know what was the value of the Doppler shift.
oh yeah, okay. I should have included that. The value of the Doppler shift in this one was about 400 kilohertz. Yeah, yeah.
Yeah.
But it's constant.
Yeah.
So your carrier is going to be sitting, oh, it's over there, but it's going to stay over there. It's not going to be changing that much.
No, not changing that rapidly.
It's amazing.
Yeah. Now, as far as the speed of these spacecraft are interesting too. Juno, which is one that I'm after at the moment, which I think my system and perhaps the operator is beyond ever detecting. Juno orbits Jupiter. Jupiter currently is at 908 million K, not too far off a billion K. I've been trying for the last month to see if I can get something. I sort of think that I should, but anyway, I haven't been able to detect it. But Juno, like most spacecraft orbiting planets, they orbit it in polar orbits, so that the orbit goes over each pole. And the reason for that is that they can get a better spread of information, or better spread of data, or whatever data they're looking for. The spacecraft orbiting Jupiter, which is an elliptical, they're all elliptical orbits. The Jupiter one, I think, is 6,500 K by, I think, about 5,000 K. And the speed of the spacecraft, as it comes back towards Jupiter, is 265,000 kilometres per hour. So it's really, yeah, I wouldn't want to hit anything. It's not, it was for a while the fastest man-made object ever. But the fastest man-made object is another spacecraft in the solar system, which is currently orbiting at 670,000 kilometres per hour, 2/3 of a million K per hour. Anyway.
How many spacecraft can you, are there in the deep space?
How many are capable of diameters?
Yes.
Yeah. At this frequency, X-band 8.5 gigs, within reasonable range of amateurs, there's probably, my estimate would be about 30. Yeah, maybe around about 30. Yeah, I have 9. I got a new one yesterday. So you might say, well, 9 and 5 months is not. It's not that as if I spend hours per day on it. I've got 4 at this range, and some a lot closer. I think I'd say there's probably about 30. Might be 20 or so on 2 gigs. Not many at 32 gigs. Maybe I doubt if there was half a dozen.
Trevor, did you say that the 32 gig satellite or probes had been detected by amateurs
Yes,
as well?
yes, they have. Amateurs singular. One amateur.
What?
Yeah. And I've just forgotten his call. His name is Graham. Lots of Grahams in England, I guess. G8 something. He did it. He did it with bits and pieces, which he all cobbled together. Built his own feed. He didn't actually make any transverters, but from various bits and pieces, he was able to do it and prove that it works. And to me, that was quite a feat. There's quite a bit of satisfaction in doing it just with buying things off the shelf. Never mind getting a mixer here or an oscillator there, etc., and a preamp. So yes, one amateur has copied it, and the results were very good. Quite a strong signal, and it was from this sort of distance as well, around 300 million K.
Have we got any questions from anybody coming in remotely? We haven't had the speakers up. John or Peter out there, any questions from either of you?
Look, if it's something that I can really recommend, if someone's looking for a new project and they might probably have already been involved in 10 gig terrestrial work or 10 gig EME, and the step up to this is not that difficult. If it's something that you want to do, I can really recommend it. Even if you just for the sake of having the piece of paper on the wall.
So what sort of data rates do they run, say, that signal when it's...
The data rates?
Yeah.
Up to, from about 40K a second, up to about 1.5 megabytes per second.
Yeah, a lot of data coming down.
Yeah, a lot of data.
Pictures, yeah.
And the high data rates, as I mentioned earlier, come, as might be expected, at a reduction in carrier.
Yeah.
Now, some spacecraft, Maven is one of them, never transmits any carrier at all. It'd be nice if NASA or European Space Agency had, for the benefit of amateurs, put a CW beacon on these things. But
I see Andrew's got his hand up there. Did you have a question or a comment, Andrew?
Could I ask Trevor something?
you might have to relay that to me.
Okay, he's not coming up. Andrew, you may be muted at the moment. We're not hearing any audio from you.
Oh, well, that's good. It might have been a question I couldn't answer.
That's it. You're there. Yeah. How do you point the antennas? What mechanism have you got for aiming and pointing?
The system I use is as per the EME system. For elevation, I used an inclinometer that I bought many years ago, 20 years ago, from the US. It's called an Angle Star. They are available. There is an agent in Australia for them, but at an exorbitant price. The trip across the ocean, for some reason, increases the price by about 3 times. But that's very accurate. I have measured its accuracy, and from on the horizon, 0 degrees elevation to 90 degrees, it's better than half a degree, which is pretty good. For azimuth, I use a prop pitch motor, World War II prop pitch motor, which is a great rotator. They used to be very, very popular in the days when there were plenty available. Prop pitch motor is a three planetary gear sets cascaded. The ratio is 10,000 to 1, or nearly 10,000 to 1. And the feature of the prop pitch is that there's virtually no backlash. They're as good as a slew drive using a special type of worm gear. So that that determines the azimuth. For position reporting, I have got driven off the main shaft a magnetic encoder. It's called an HH12, quite cheap. I think they're about $30. And I've got a unit made by a German amateur to read that data that comes down from that into 0.1 degrees resolution. That's not all that great. Over the azimuth range that I use it at, which is about 100 degrees, it's good to within about 2 degrees. Now, 2 degrees in terms of accuracy is not that good, but it's okay. If I'm on a spacecraft, I can just move it within 2 degrees. I've got it set up so that the error, whether it be half a degree or 2 degrees, is always in one direction. In other words, I don't say, let's go left, is it left or is it right? It's always going to be in one direction. It just depends on how much. So I offset it to start with. But you can get better systems. There's an amateur N8 something Q markets a controller called a green heron. You've heard of those? Yeah. Okay, they're very popular. They're quite expensive. I did look into it at one point, but the cost was pretty exorbitant. So I just rely on what I've got, and it's pretty accurate. It wouldn't be any good for Canberra with a 0.04 half-power beam width, but it's okay for me. 3.7 metre dish at this frequency has a 3 dB or a half-power beam width of about a bit better than 1 degree, about 0.7 degree on paper. And this is going by the VK3UM calculator. Now, by my measurements, my system is broader than 0.7 of a degree, which does say something. So possibly the 3.7 metre dish is in fact acting more like maybe a 3 metre dish. I haven't really bothered to optimise it. The broader half-power beam width suggests that the dish is being under-illuminated. Now, I'm quite happy with that, because if it's under-illuminated, you're not getting much spilling over the edges. And anything, of course, spilt over the edge is going to induce noise, because that amount of RF is going to see ground, especially at high elevations. The higher the elevation, the better angle you've got at the ground. So, whilst not an optimum setup, I think what I've got's all right.
Well, you had a question.
I'm wondering about some spacecraft fly close to the sun. But amateurs finding it difficult to look at Parker Solar Probe.
That's right. If the sun was in the background, yes, it would kill it. Some noise would definitely kill it. With the system that I use, I've described, I'm currently sun noise. There's a lot of sun activity responsible for the recent Southern Lights aurora. The system I've got currently with a solar flux index of 160, I'm seeing about 16 dB of sun noise over and above. Yeah, so no weak signal is obviously going to compete with that, but or anything like it. Even moon noise, the 1 dB of moon noise that I get would be undesirable. 1 dB above the noise is a figure that you can the human ear can just hear. As you go over it, you can just detect that it's got a slight noise level increase.
100 kilohertz.
So, looking at the sun, what you must be doing then is looking at it side on. In other words, there's no conjunction involved. The spacecraft is not in between the receiving station and the sun itself. If it was, you would be looking.
I mean, some are naturally close anyway. Parker Solar Probe and orbiting Mercury.
Yeah, they go surprisingly close.
Yeah.
Yeah. It would be nice to put a figure on that. Only a few million K, I think. Sun's distance does vary, but nominally it's about 150 million K. Now, these spacecraft that cruise by the sun, of course, have got to be pretty special with regards to heat shielding, and not only that, radiation shielding as well.
Well, there we are.
I don't think I've got anything else to offer.
All right. Well, thank you, Trevor, on
Thank you,
behalf of
Trevor.
all of us.